Hello class, today we're going to be going over Module 11 homework, and Module 11 is on quadratic functions and higher ordered polynomial functions. So basically any polynomial to the second degree or higher. So this is kind of a long homework, so I'll try to go through this as quickly as I can. Let's get started. So number one, a water rocket can be purchased at many toy stores. One company claims that the height above the ground in feet for the rocket t seconds after it is launched can be modeled by s of t. So what is the maximum height that this rocket can reach? Well, this is nice because the function is given to us in vertex form. In vertex form for quadratic can be written as y equals a times x minus h squared plus k, where hk is the vertex, either the highest point of a quadratic or the lowest point of a quadratic. So what is the maximum height that this rocket can reach? Well, in this case, this is a negative quadratic, so our function is going to look something like this. So we are talking about a high point, and that makes sense. This is an arc, creates an arc. We're talking about the height of a rocket over time. It goes up, it hits a maximum point, and then it goes back down. So that's going to be our h of k, that high point. So the maximum height, well, that's going to be the k value of it. That is our height in feet. So that's going to be 66 feet. And then how long is the rocket in the air when it reaches that height? Well, that's going to be our h value, and in this case it's 2, so after 2 seconds. Then determine the vertical intercept of the function and explain its meaning in the problem context. Well, think, the vertical intercept happens when the x value is 0, so I just need to evaluate this function at 0. So s of 0 is equal to negative 16 times t minus 2 squared, 0 minus 2 squared, plus 66. And simplifying this, let's see, we get negative 16. Negative 2, this is going to be negative 2, so negative 2 squared is 4, plus 66. Negative 16 times 4 is negative 64, plus 66 is 2. So our vertical intercept is 2, and that just means that the rocket is launched from a height of 2 feet. Remember, our y value is our height, and this is when x equals 0, so it's when it's first launched. It's launched at 2, it's launched from 2 feet. So I guess we could say the rocket is launched from a height of 2 feet. Okay. And then D, determine the horizontal intercepts and explain their meaning in the problem context. If they do not have a meaning in the problem context, explain why not. So we're going to use Desmos for this. And I went ahead and I graphed the function on Desmos. And we get a, we get a quadratic. So let's talk about its x-intercepts. It looks like the x-intercepts, we have 2 of them, or our horizontal intercepts. One is at negative 0.3. or negative 0.03, and our other one's at 4.03. So those are our 2 horizontal intercepts. And explain their meaning in the problem context. Well, let's think about it. This first one has no meaning. If we just zoom in onto this function here, notice that our first intercept happens in the negative time area. Anything to the left of 0 is in negative time. So that doesn't make sense. So the first horizontal intercept has no meaning for that reason. The second one, though, that's in positive land of our x values. So what that means is this horizontal intercept is when the rocket lands, and it's at 4.03 seconds after it took off. So The second horizontal intercept is when the rocket lands. And that's going to be 4.03 seconds after launch. Okay. Let's go to number 2. So the function f of x is a quadratic function written in factored form. We can see that when x equals 4, f of x is 0, and when x is negative 1.75, f of x is 0. Hence, the points 4, 0 and negative 1.750 are often referred to as the zeros of the function, or the roots. From your previous work, you know that these points are also the horizontal intercepts of the function. So explain or show why f of x of 0, or f of x equals 0 when x equals 4. Well, let's think about it. You know, my marker here is running out. I'm going to change colors. So if we plug in 4, so f of 4 is going to be, let's see, equal to 3 times 4 minus 4, 4 plus 1.75. So we're going to get 3 times 0, that's 4 minus 4 is 0, times 5.75. And notice anything that when we're multiplying, and if one of the factors is 0, the whole thing is going to zero out on us. So that is y. And likewise, the same goes for when we plug in negative 1.75. We have 3 and then negative 1.75 minus 4 times negative 1.75 plus 1.75. And notice this last factor zeroes out on us. So we're going to have 3 negative 5.75 times 0. And again, if 0 is a factor of any product, the product is always going to be 0. So that's why. C, convert this formula to standard form by distributing and combining like terms. So let's see, we're just going to multiply all these factors together. And I'm going to go ahead and multiply these second two factors together first. So I'm going to multiply this to both of these and this negative 4 to both of these in the second. So I want to multiply everything together. So we have 3 times x is x squared. X times 1.75 is 1.75x. Then negative 4 times x is minus 4x. And then negative 4 times 1.75 is negative 7. And then I just need to distribute that 3. So this is going to be 3x squared plus, let's see, let's combine like terms first to make our lives easier. We have two x terms. So we're going to have 3 times x squared minus 2.25x minus 7. And then now we can combine like terms, or now we can distribute this 3. So I'm going to multiply the 3 to all of these terms. So we're going to have 3x squared minus 6.75x. That's 3 times negative 2.25x. And then 3 times negative 7 is minus 21. So now we have it in standard form. And state the vertical intercept of the function. Well, what's nice about standard form is our constant value is the vertical intercept. So our vertical intercept is 0, negative 21. So that's the thing to know there. In standard form, our constant is our vertical intercept. So moving on to page number 2. Excuse me. In 2008, or the 2008 Men's Olympic shot put event was won by Poland's Tomasz Majewski with a throw of 70.57 feet. The path of his winning throw can be approximately modeled by the quadratic function defined by v of h, where h is the horizontal distance in feet from the point of the throw, and vh is the vertical height in feet of the shot above ground. So A, determine the vertical intercept and explain its contextual meaning. Well, the vertical intercept, this is in standard form, so our vertical intercept is just going to be 0, 6. Well, I need to plug in my computer. Okay, so our vertical intercept is 0, 6. And the shot put, that just means that the shot put was thrown from 6 feet off the ground. Okay, because the V of H is the height. Okay. So B, determine the horizontal intercepts and explain their meaning in the problem context. If they do not have a meaning in the problem context, explain why not. So we're going to use Desmos for this again. And I went ahead and I graphed this function. Let's see, I'm just trying to get this so it looks a little nicer. Okay. All right. So our horizontal intercepts, we have one at negative 5.53, 0, and one at 70.57, 0. Let's go ahead and write those down. And again, in this case, our first horizontal intercept is negative. It wasn't thrown from the ground. Well, it's negative. It's negative feet in this case, and so this doesn't really make sense because we know that it was thrown from 6 feet off the ground. So the first horizontal intercept has no meaning. The second one, though, the second one does have a meaning, and it shows that the shot put hit the ground 70.57 feet horizontally from when it was thrown. Remember, in this case, our H values don't represent time. This represents the horizontal distance in feet. So these represent horizontal distances. So our second horizontal intercept shows that the shot put hit the ground 70.57 feet horizontally from where it was thrown. Okay, and then determine the vertex and explain its conceptual meaning. So, here's the thing about quadratics. Quadratics, they have symmetry. So, what's on the left side of the vertex is the exact same as what's on the right side. It's just a reflection of one another. So, that means if we have a function like we do, right? Well, a quadratic function like we do, that means the vertex is right, or the x value of the vertex is right in the middle of our two horizontal intercepts. So if we just find the middle point, which if we'd add these two together and divide by 2, we get 32.52. So that's the x value of the vertex. To find the y value, we want to plug this x value in. So v of 32.52, if we were to do all the math, we would get out 22.26. So our vertex is going to be 32.52, comma 22.26. And what that means is that the shot put had a maximum height of 22.26, and that happened when it was 32.52 feet horizontally from where it was thrown. because remember, we're not dealing with time anymore. This is strictly position. So the shot put had a max height of 22.26 feet, and that occurred at, or when the shot put was 32.52 feet horizontally from where it was thrown. Okay. Then determine the practical domain and range. Well, the domain, that's our x values. That's going to just be from 0 to wherever it landed. So from 0 to 32.52. And our range would be from 0, the ground, to its max height, which was 22.26. Awesome. And then part E, determine the horizontal distance of the shot when the vertical height is 8 feet. So, again, I graphed this onto Desmos. And here we have our function in red, and then in blue is y equals 8. So that's at 8 feet. So we want to know our intersection points. And it looks like our intersection points are when h is equal to 2.066 and h is equal to 62.975. So, what does that mean? That's the horizontal distance when the height was 8 feet. So we threw it up. After 2 feet, it was at 8 feet, and then it came back down. After 62 feet, or almost 63 feet from when it was originally thrown, it was at a height of 8 feet as well. So, moving on. All right. Number 4, given g of x, determine the zeros. Well, the nice thing about functions in factored form, this is factored form. Notice it's composed strictly of factors. Is that if we set each factor equal to 0 and solve for each x, those are our zeros. So if we take 3x plus 15 set equal to 0, and then x minus 3 set equal to 0, solve for each x, those will tell us the two zeros. So here we'd subtract 15 from both sides. 3x equals negative 15. Divide both sides by 3. Oh, got ahead of myself. Negative 15. X is equal to negative 5. And then here you can just see we add 3 to both sides. X would equal 3. So those are the two zeros, or the two horizontal intercepts. B, to determine the vertical intercept. So again, the vertical intercept happens when x is 0. So let's just evaluate this thing at 0. Which will give us, this zeroes out, so we're just going to have 15 times negative 3, and that gives us negative 45. So our vertical intercept is at 0, negative 45. And then determine the vertex. Again, remember the vertex is right in the middle of our two zeros, of our two horizontal intercepts. So if we just add them together and divide them, we should get the point, or the x value, where the vertex lies. So negative 5 plus 3 divided by 2. It's going to be negative 2 divided by 2, which is negative 1. And then evaluate to find the y value, evaluate when x is negative 1. So g of negative 1 equals 3 times negative 1 plus 15 times negative 1 minus 3. Let's see, this is going to be negative 3 plus 15 and this is -4. And let's see, so -3 plus 12, that's 9. No. Oh, I got ahead of myself again. It's 15. Oops. -3 plus 15 is 12. Times -4 is -48. So the vertex is a -1, comma, -48. Just like that. All right, moving on. So for number 5, for each given graph, we need to label concavities, inflection points, and relative extrema. B, label any relative extrema as absolute if they exist. And C, describe the end behavior of the function. And D, explain what degree polynomial the graph could be and why. So, concavities. Concavity, is it opening up or is it opening down? That's what concavity is. So let's first start with our inflection points, because our inflection points are the division lines between our concavities. So think back when we dealt with inflection point of a logistic function, right? The inflection point would happen right there in the middle of the curve where the rate of change of the rate of change changed. So remember from logistic, it looks something like this, where it was increasing at an increasing rate, and then it started decreasing at a decreasing rate, right? So this would be our inflection point, okay? And this side would be concave up, like a cup, if that's a good way to remember it, and this side is concave down. So let's start with the inflection points. So we're going to have an inflection point right here, and right about there. So these are our inflection points. And then let's do relative extrema. So that's going to be the highest or lowest point, not necessarily, not of the whole function necessarily, but just of a given area. So we see here, this is going to be a local max. The reason it's not an absolute max is that it's not the absolute highest or absolute lowest point of the function. Notice that this little section here goes higher. So, and this is a relative extrema. Relative, it's local, right? It's not absolute. And then we have this down here. This would be our local min. And this is also a relative extrema. So now let's talk about concave up and concave down. So I said that the inflection points are the dividing lines between the concavities. So we have something right here, another one right here, changes here, and then we're good. So this whole left side, and then this little bit in here, this little bit, and then this whole right side. So concave down, concave up, it's pretty self-explanatory. Earlier I said it's like a cup. Concave up is like a cup. It can hold water, if you will, right? So, so this first part is concave down. This little middle part right here, this is concave up. If you can see it, it kind of goes up like the edge of a cup, right? So I'm going to write this on the side. Concave up. And then this next part is concave down. It's like an upside down cup, right? Or the side, or one half of an upside down cup. So this is going to be concave down. And then this next portion is all concave up. All right. And then let's see here. So let's Oh, and part B, label any relative extreme as absolute. We discussed that none of these are absolute maxes because this is an absolute because this portion goes higher. This is an absolute min because this portion goes lower. So we're done with A and B. Let's go on to C. Describe the end behavior of the function. So the end behavior, let's see, we can say the graph has opposite end behavior because look, as we go to the right, it goes up forever, and as we go to the left, it goes down towards negative infinity. So when you say the graph has opposite end behavior. And we would write that as, if you remember these two statements, as x approaches infinity, f of x approaches something, and as x approaches negative infinity, or as we go to the left, f of x or y approaches something. And in polynomials, it'll always either be positive or negative infinity. So let's see, as x approaches infinity, as we go to the right, as we take this towards x infinity direction, the f of x is also approaching infinity, positive infinity. And then as x approaches negative infinity, as we take this thing to the left all the way, f of x is also approaching negative infinity. So that's our end behavior. Notice they go in opposite directions. One goes up, one goes down. And then part D, explain what degree polynomial the graph could be and why. Well, to me, this could be a 5th degree polynomial. And there are a few reasons here. One of the reasons, it has opposite end behavior. That will happen for odd degreed functions. So think 1, 3, 5, 7, 9, right? If that's your highest exponent. And also there are 4 concavities, right? 1, 2, 3, 4. And the way the concavity works is, I'm out of focus here. There we go. The way that concavities work is that how would I put this? The degree of a polynomial is, well, no, a concavity, the number of concavities can't be more than 1 less of the degree. So because this is a 5th degree polynomial, we would expect to see no more than 4 different concaves. So that kind of gives me a hint that it could be 5th degree as well. There are 4 concavities. And then finally, there are 3 inflection points. And the inflection points work the same way, where the number of inflection points can't be more than 2 less of the degree. So because 3 is 2 less than 5, that kind of gives me another idea that this could be a 5th degree polynomial. Okay, excuse me, so let's do the same thing with the second graph. So label concavities, inflection points, and relative extrema. I'm going to label the inflection points first. So we have one right here and one right here. And let's see, let's go into concavities. So remember, the inflection points are the dividing lines of the concavities. So we have this whole left side, we have a little section in the middle, and then on the whole right side. So this left side, this is concave down. This little middle portion is going to be concave up. And this last section to the right is all concave down. All right, and then relative extrema. So we only have one right here. Notice that it goes down on both sides. But this isn't a relative. This is actually going to be an absolute extrema. It's an absolute max. Because notice that the function doesn't go any higher than this point. So this we can say is an absolute max. And it's classified as an absolute extrema. Okay. So part C, what about the end behavior? So let's describe the end behavior. So this graph we would say has, you can think of it as having the same end behavior regardless of what direction we're going, whether we're going to the left or to the right. This function goes down in both directions. So we say the graph has the same end behavior. And then as far as our statements go, as x approaches infinity, f of x is approaching what? And as x approaches negative infinity, f of x is approaching what? So what happens as we go to the right is that what the first statement is saying, and then what happens as we go to the left, which is what the second statement is saying. Well, in this case, we discussed they both are going down. So they're both approaching negative infinity. So as we go to the right, this thing is going down. And as we go to the left, it is also going down towards negative infinity. All right, and then part D, explain what degree polynomial the graph could begin. Why? Well, this could be a fourth degree polynomial. And this is why. Well, they have the same end behavior, and that happens for all even degree functions. So think of quadratics or something to the 4th power, 6th power, 8th power. All of those, the ends will tend towards the same direction, either both up or both down. And then in this case, there are 3 concavities. And remember what I said earlier about concavities. Concavities can't exceed 1 less than the degree of the polynomial. So because there's 3, kind of gives me the idea that it could be a 4th degree polynomial. And then finally, there are 2 inflection points. And as I said earlier, the inflection points can't exceed less than 2, or can't exceed 2 less than the degree. All right. So now we're on to the last page. All right, the per capita consumption of breakfast cereals, ready to eat and ready to cook, since 1980 is given in the table below. So part A, make a scatter plot of the data, and using the idea of rate of change, explain why the cubic polynomial function best models the data. So compute the model C of t and round your parameters to 3 decimal places. Okay, so I went ahead and I graphed this one as well. And I'll turn off my old ones and then I'll... So this is the data right here. Notice that it starts concave up, and then right around this point there's an inflection point, and then it kind of goes concave down. So that's a good indication that it could be cubic, because a cubic function would have that as a portion in it, where you go concave up and then concave down. So I went ahead and I got the line of best fit. As you can see, it looks pretty nice. It models the data pretty accurately. And the r squared is very close to 1. So that tells me it's pretty accurate as well. And these are my parameters. So my function, it's a cubic, so I'm going to start with my x cubed term. Let's see, it's going to be C of t is the name of this guy. So negative 0.005 t cubed plus 0.123 t squared minus 0.376 t and then plus 12 0.112. So that's our function, and explain why a cubic polynomial function best models the data. Because of the concavities. Because of the two concavities. We have one section that's concave up, and then one section that's concave down. And quadratic and all the others don't have that special quality of the two concavities. Okay. B, compute C of 20 and explain what the result means in the context of the data. So C of 20, we would just plug in 20 and simplify. We would get 13.197. So what that means is 20 years from 1980, that would be the year 2000. So in 2000, the per capita consumption of breakfast cereals was 13.197 pounds. So in 2000, the per capita consumption of breakfast cereals was 13.197 pounds. Okay. And then C, using the model, solve C of t equals 16, explain what the result means in the context of this data. So I took the function as well, and then, let's see, I'll have to do, I guess I deleted it. There we go. So in red we have the equation C of t equals 16, and we want to know, we want to solve it. So that means where they intersect. So I'm only going to look at the positive ones in this case. So they intersect when t is equal to 10.615, and when t is equal to 18.044. Okay, so explain what the results mean in context. So basically what that means is in the year, 10 years after 1980, so in 1990, and then 18 years after, 1998, the per capita consumption of cereal was this 16 pounds. So in 1990 and 1998, per capita consumption was 16 pounds. Okay. And then part D, determine any local extreme values and explain what they mean in the context of the situation. So, we have, let's see, I'm going to turn off all these other points here. We have 2 points. We have two extrema here. We have, they're both local or relative. So at this point, we have a local min. So local min is going to be at 1.706, comma 11.804, and then we have a local max at, well, this point up here. That's going to be 14.694, comma 17.281. Okay. And what do they mean in the context of the situation? Well, let's see. 1.7, or well, about 1 year after 1980, the consumption of cereal hit a low point, and then about 14 years after 1980, so in 1994, the consumption of cereal hit a high point per capita. So in 1981, per capita consumption was at a low, And in, let's see, 14 years after, in 1994, per capita consumption was at a high. So awesome. And then E, describe the in behavior for the function model and discuss whether or not you think this in behavior will accurately predict future consumption of breakfast cereal. So let's go over this. Let's write our little statements again. So as x approaches infinity, f of x approaches something, and as x approaches negative infinity, f of x approaches something. So as we can see, if I were to zoom out a little bit, maybe it would be better. As x approaches infinity, as we go to the right, f of x is approaching negative infinity. And as we go to the left here, as x approaches negative infinity, f of x approaches positive infinity. So again, this is an opposite in behavior kind of function. So as x approaches infinity, f of x approaches negative infinity. And as x approaches infinity, f of x approaches positive infinity. But we're only going to really talk about the positive in behavior here because that's what the model models. Let's see. Do you think this in behavior will accurately predict the future consumption of breakfast cereal? No. Because future consumption can't be infinity or negative infinity. Or negative in that case, right? We know immediately at this point, we know for a fact that after this point, the function doesn't make sense because we can't have negative consumption. That would just be strange. So, and then part F, consider the equation C of t equals 0. Provide a mathematical argument for the solution to this equation. You may use a function, its graph, and or a table in your argument. Also provide an argument as to why this equation may have no real world meaning. So, here I have the two functions. I have our model in the black, and then C of t equals 0 in red. So provide a mathematical argument for the solution. So the solution is just where they intersect. So in this case, it's when t equals 25.395. So that's our solution. We looked at it graphically. That's all right. And then also provide an argument as to why this equation may have no real world meaning. Well, let's see. Will the consumption of breakfast cereal ever get to 0 per capita? And that's probably not ever going to happen. So this has no real world meaning because it's saying that 25 years after 1980, so by 2005, per capita consumption of cereal would be 0. And I don't think that would happen. So that was the homework for this week. Hopefully this helped going over it, and have a good day. Bye.